Hello everyone. Our research is titled Vision-Based Object Classification using Deep Learning for Mixed Palletization Operation in Automated Warehouse Environment. The research was conducted at the Robotics Innovations Lab, Center for Product Design and Manufacturing at the Indian Institute of Science. The presentation is divided into 5 different parts: problem statement, method overview, method description, experiments and results, and lastly, conclusion and future work. Typical jobs in warehouses are very labor intensive and have high risk of injury. Automation has the potential to improve the efficiency and throughput of operations while also lowering cost and increasing safety. For complete warehouse automation, fast and reliable methods are required for object classification and object dimension extraction. Object classification methods would allow us to automate inventory tracking in warehouses. Object dimension extraction method will allow us to automate the palletization process. In this research, two purely vision-based methods are presented to address these requirements. Start with the method to extract object dimensions. In a warehouse, the incoming items are placed on pallets which are then stored on racks. It is a very labor-intensive work. To perform palletization, a robot would need to identify the dimensions of the incoming object and then arrange them on a pallet based on a pre-computed pattern. An example of a pre-computed pattern is given in figure 3. We give a brief overview of the proposed method for object dimension extraction. First, let's go through the assumptions made for this method to work. We have assumed that the camera coordinates are fixed and the background behind the object in the image is composed of a single color, and this color is contrasting to the color of the object. The proposed method consists of 3 different steps: background removal step, object boundary extraction step, and real dimension calculation step. Here, we have shown the process flow diagram for the proposed method. In the following slides, I'm going to briefly describe the steps involved in the method. A color space is a mathematical model describing a way to represent the color as a tuple of numbers. There are many popular color spaces such as RGB, HSV, YUV, etc. The input image is converted from RGB color space to HSV color space because in RGB color space the color and intensity information are mixed, which is not suitable for image segmentation. During the calibration process, the range of HSV components belonging to the background is determined. A pixel is defined as a part of an object if its 3 HSV components not all lie within this range. The thresholding operation is formally described in equation 1. Figure 7 shows the result of color thresholding on the image. The original image is shown on the left hand side and the final image on the right. In the final image, we can see that the color thresholding has effectively removed the background from the image. Gaussian blurring is a procedure to blur images and remove noise. It involves convoluting an image with a Gaussian kernel. The Gaussian kernel coefficients are sampled from the 2D Gaussian function. A 5x5 Gaussian kernel with sigma equals 1.1 was used in this method. Figure 8 shows a plot of the Gaussian function used to generate the kernel. Figure 9 shows the effect of Gaussian blurring on an image. Unlike regular thresholding, which uses a global threshold value, adaptive thresholding uses a different threshold value for each pixel in the image. This threshold value can be calculated in multiple ways. The method utilizes the Gaussian
weighted mean of the 11 cross 11 region around the pixel location to calculate the thresholding value for each pixel. A constant number c equals to 2 was subtracted from the weighted mean to obtain the threshold value. Equation 3 and 4 formally describe this adaptive thresholding operation. Figure 10 shows the result of the adaptive thresholding. The middle image is the input to the adaptive thresholding operation, and the rightmost image is the output of the operation. The object boundary is extracted using adaptive thresholding. Erosion is a morphological operation in which a kernel is scanned over the image. The minimum pixel value overlapped by the kernel is computed, and the image pixel under the anchor point is replaced with this minimal value. The method utilizes a 3x3 matrix of all ones as the kernel. Figure 12 shows an example of the erosion process on a grayscale image. Figure 11 shows the result of erosion. The middle image is the input to the erosion operation, and the rightmost image is the resulting image after the application of the erosion operation. Contours are curves joining all the continuous points along the boundary having the same color or intensity. Contours provide information about the shape of the object. A rotated rectangle of minimum area, including all the points on the contour, was found. The sides of this rectangle were calculated. Figure 13 shows the contour created by the object boundary. Figure 14 shows the rectangle of minimum area, including all the points on the contour. The real dimensions of the object, represented by R1 and R2, were calculated by multiplying the sides of the minimum area bounding box, represented by D1 and D2, with the conversion factor obtained during the calibration process. Conversion factor is the ratio of the distance of 2 points in the real world to the distance of the same 2 points in the image. Equation 5 and 6 depict this formally. The calibration process involves determining the range of HSV components of the background and the conversion factor, the ratio of the distance of 2 points in the real world and the distance of the same 2 points in the image. For determining the range of HSV components, an image without any object in it, with only background, was taken, and the minimum and the maximum value of all 3 components in the entire image was calculated. Figure 17 shows the histogram of all 3 HSV components in the background. For calculating the conversion factor, an object with known dimensions was taken. Using this method, the length of the sides of the rectangular bounding box of this object was calculated. Then the conversion factor was calculated as the ratio of the real dimension of the object and the dimensions of the bounding box. Equation 7 describes the conversion factor calculation formally.
Let's move to the second method for object classification. In warehouses, it is necessary to identify incoming and outgoing items for keeping track of the inventory. Barcode and RFID tags are the typical ways to identify the incoming and outgoing items, but both of them suffer from limitations. Barcodes easily get damaged, and most barcode scanners require manual operation. RFID tags have limited lifetime. Both RFID tags and scanners are costly.
The steps involved in the method are depicted in figure 4. The method consists of 3 steps: data preparation step, model training step, and image prediction step. Each of these steps are described in detail in the following slides. Our convolutional neural network utilizes a special type of network architecture called residual network, or ResNet in short. Traditional convolutional neural networks pass the output of a layer as an input to the next layer. Residual networks add an additional skip connection between the two layers, bypassing the non-linear transformation. Residual networks are easier to optimize compared to traditional CNNs. Their performance improves with increasing depth. A dataset of 1427 images of 6 different categories of machine parts was created. These machine parts include a Dobot charger, Dobot gripper, Dobot pen holder, Dobot 3D printer nozzle, Dobot 3D printer extruder, and Dobot suction cup. The training set consisted of 955 images and the test set consisted of 472 images. The images were taken from a 48 megapixel camera with GM1 sensor and f1.8 aperture lens. In indoor conditions, the camera was mounted on a stand at a height of 40 cm and the objects were placed underneath it. The camera was connected to a computer with Intel Xeon CPU with Tesla K80 GPU and 12 GB of RAM. Experiments were also performed on the same computer. The model was implemented in Python using Keras. All 6 different categories of machine parts are shown in figure 7. Our dataset consists of approximately 1.5 thousand images. The size of the dataset is quite small. Deep neural networks require more data compared to other machine learning approaches. To increase the size of our dataset, we utilize data augmentation. Augmenting an image dataset can be done by multiple techniques such as affine image transformation, color modification, and even generative adversarial neural networks. Since the dataset consists of only 955 training images, a combination of affine image transformations such as shift, rotation, zoom, and reflection, and color modifications such as contrast and brightness we utilized during the training to achieve better result. Figure 9 shows the result of application of affine image transformation and color modification. The fully connected layers at the end of the pre-trained ResNet 50 were removed since the dataset has only 6 classes while the ImageNet has over 1000 classes. 4 new layers were added at the end of the model. Flattening layer, fully connected layer of 256 neurons with ReLU activation function, followed by a dropout layer with probability of retaining set to 0.5, followed by a fully connected layer of 6 neurons with softmat or activation function. Figure 11 shows the newly added layers in detail. The input images were resized to the size of 224 cross 224. Categorical cross entropy was used as the loss function. Equation 1 shows categorical cross entropy. In equation 1, Pi is the predicted probability of the image containing the ith object. And similarly, Ti is the true probability of the image containing the ith object. A learning rate of 0.0001 was used with stochastic gradient descent as the optimizer. The model was trained for 30 epochs. Figure 12 shows the variation of loss function, namely categorical cross entropy, during the training process. 3 different experiments were performed to investigate the characteristics of the proposed method. The images for the experiments were taken from a 48 megapixel camera with GM1 sensor and f1.8 aperture lens in indoor conditions. The camera was mounted on a stand at a height of 40 cm and the objects were placed underneath it. All the experiments were performed on a computer with Intel Xeon CPU with Tesla K80 GPU and 12 GB of RAM. The proposed method was implemented in Python using OpenCV. The result of the experiment is given in table 1. The average percentage error in all 125 images was 6.492%. Among all the objects, when pen was used for calculating the conversion factor during calibration, the average percentage error in the prediction was minimum at 4.514%. When Dobot extruder was used for calculating the conversion factor, the average of the percentage error in all 125 images was at 12.063%, the maximum. This is likely resulted because of the large difference in the height of the extruder 55 mm and other objects. The mean height of other objects were 8.75 mm, which caused the extruder to appear bigger in the image than it actually was. Therefore, for the best results, the object with height closest to the mean of the height of all objects should be chosen for calculation. The prediction time is defined as the compute time or runtime that the method takes to make a prediction on an image. Average prediction time is defined as the mean of the prediction time on all images. The speed of the algorithm in frames per second is expressed as the inverse of the average prediction time. To calculate average prediction time, the algorithm was made to run on 125 images, 25 images per object, and for each object, the average time the algorithm took for prediction was noted. The algorithm roughly took the same time for all objects, around 4 milliseconds. The algorithm can be made to run at 250 frames per second. Another experiment was performed to evaluate the effects of the camera resolution on percentage error in prediction. The algorithm was made to run on 125 images, 25 images per object at 5 different resolutions: 1000 into 750, 800 into 600, 600 into 450, 400 into 300, 200 into 150. The average percentage error at each resolution was noted down. The result of the experiment is given in Table 3. The average percentage error decreased with the increase in resolution, which can be understood by the fact that an increase in resolution accompanies an increase in the detail of the object in the image and allows for creation of more accurate bounding box. Two different experiments were conducted to evaluate the accuracy and speed of the proposed method. Before we move on to the experiment, let's first define the metrics involved. Three parameters were utilized to judge the performance of the solution: accuracy, precision, and recall. Accuracy is defined as the ratio of the number of correct prediction to the number of total predictions. Precision is defined as the ratio of the number of true positive results divided by the combined sum of the number of false positive results and the number of true positive results. Recall is defined as the ratio of number of true positive results divided by the combined sum of the number of true positive results and the number of false negative results. 472 images present in the test dataset were used to calculate these parameters. In the experiment, the accuracy of the model came out as 98.94%, approximately 99%, which is impressive given the small size of the datasets utilized. The recall and precision of the model were consistently above 90% for all the categories. Based on the result of the experiment, the confusion matrix was calculated. The confusion matrix is given in figure 17. The confusion matrix is a table that allows visualization of the performance of a supervised learning algorithm. Each row of the matrix represents the instance in an actual class, while each column represents the instances in a predicted class. From the confusion matrix, we could infer that the model seems to confuse between Dobot charger, Dobot pen, and Dobot suction curve. Another experiment was conducted to evaluate the speed of the proposed method. In this experiment, average prediction time was defined as the mean of the prediction time, the time taken by the model to generate a prediction on an image. The average prediction time calculation is shown in equation 5. To calculate average prediction time per object category, prediction on 150 test images, 25 images per object were made, and for each object category, the mean of the prediction time was noted. The results are shown in Table 3. The average prediction time came out to be about the same for each object. Hence, the speed of the method is independent of the object in the image. The average prediction time over all the object categories was calculated as the mean of the prediction time over all images. This came out to be 0.23 seconds. Here is our proposed method in action. A small data set consisting of 6 images is chosen for this demonstration. Let's look at those images. These 6 images were chosen for this demonstration. The name of the object present in each of these images are given above them, along with the dimensions of the object. So this image contains a Dobot pen holder. The dimensions of the Dobot pen holder are 144 mm cross 57 mm. This image contains a Dobot 3D printer extruder. The dimensions of the 3D printer extruder are 68 mm cross 51 mm. Now let's pass these images, and using our proposed method, let's try to predict the dimensions of the object inside them. So we have our predictions here. The predicted dimensions of Dobot pen holder are 148 mm cross 57.95 millimeters. So that is quite comparable to the true dimensions of the pen holder. Let's look at another example. The dimensions of the predicted dimensions of this objects are 68 mm cross 46 mm. The true dimensions are 65 mm cross 44 mm. So as you can see, our method has given a good approximation of the dimensions for each of these objects. A small dataset consisting of 11 images were chosen for this demonstration. Here are the images with the name of the object present in them. These 11 images were selected for this demonstration. The name of the object present in each image is given above them. So this image contains Dobot 3D printer extruder. This image contains a Dobot gripper. This image contains a Dobot suction cup. Now we will pass this image into our model which we created in Python using Keras library. Then we will compare the predicted label on these images with the true label. This will take some time. We have gotten our result. This is the name of the object the model thinks exists in the image. As we can see, yes, this is in fact a Dobot 3D printer extruder. This is also correct, a Dobot gripper. This is also correct, a Dobot suction cup. In fact, the model has predicted correctly all of these 11 images. So we have achieved 100% accuracy on these 11 images.
In this research, two purely vision-based methods for object classification and object dimension extractions were presented. The method worked using images taken from a 2D camera. The classification method achieved a high accuracy of 98.94%. The method for object dimension extraction had an error rate of 6.5% on average. The methods ran at 4 frames per second. In the future, the method will be implemented on a robot for real-world experimentations. The method will be adapted to perform the task of object alignment and sorting. More advanced deep learning frameworks such as mask RCNN, will be employed to perform the task of classification, localization, and segmentation using a single network.